Welcome back. This is video lecture 18.2, and we're going to discuss from our book, chapter 18, section 4, which is described as absorption of heat. So the first thing we better do is define what we mean by heat. Now, heat is a form of energy, and the symbol that we use to represent heat energy is a capital Q. So we have to use that notation. But what is heat energy? Let's be clear about that. Here's my description of it. Heat energy is the thermal energy transferred, let me emphasize that word, transferred between a system and its environment because they have different temperatures. Heat energy is thermal energy that is transferred between system and environment because they have different temperatures. Again, heat energy is energy that has been transferred from one thing to another. Transferred energy. Please note then, it would be a non sequitur to talk about a single system having heat energy, because that flies in the face of what we just defined heat energy to be, as energy transferred between one thing and another. And if we're only talking about the energy transfer between one thing and another, you can't talk about it as just belonging to one thing. You can't say something like, oh, this system has, its energies would be in joules, 10 joules of heat. To a physicist, that is a meaningless statement. You could say it has 10 joules of thermal energy, that form of internal energy related to its temperature, but you can't say a system has 10 joules of heat. You could say a system transfers 10 joules of energy as heat to its environment. Okay? Okay, remember the other way we transfer energy between a system and its environment is work. Right? Work is a way to transfer energy between system and environment, and now heat is a way to transfer energy between system and environment. Work's transfer is because of a force. Heat transfer is because of a temperature difference. And just like we wouldn't say that block has 10 joules of work, we wouldn't say that block has 10 joules of heat. Okay. So, heat energy symbol Q, it is energy transfer, so SI unit will be joule, and it's energy transfer between system and environment because of a temperature difference. So that basically means there are three possible scenarios, which are represented here in the picture schematically. We have a system represented as a green blob with some temperature T sub S, and then the surroundings, or the environment, with temperature T sub E. And the first picture represents a scenario where the system has a higher temperature than its environment. T sub S is greater than T sub E. When the system has a higher temperature than its environment, experiment shows us that the energy transfer direction is from the system into the environment. And since this is because of a temperature difference, this transferred energy we call heat. Okay? And that's what this arrow right here represents, this red arrow labeled Q. And notice the direction of the arrow. It's representing an energy transfer as heat from system to environment. If you want to think something specifically in mind, suppose you had a block of, say, solid iron that you had in some kind of a big oven for a while, and then you just take it out and put it in a regular room at room temperature. Then the temperature of the iron, if we call that the system, will be higher than the environment, the room. And there will be energy transferred as heat from the block of iron into the room. That's one possibility. That's the first picture here. The middle picture shows another possibility. In the middle picture, the temperature of the system exactly matches the temperature of the environment. T sub S equals T sub E. In that case, experiment shows that there's no energy transferred as heat between system and environment, either way. Okay? No energy transferred as heat. Remember, actually, from the previous video lecture, this particular situation is somewhat special and is described as thermal equilibrium. Okay? When two objects, system and environment in this case, have the same temperature, we say they're in thermal equilibrium, and there will be no energy transfer as heat between them. The bottom picture shows the situation where the temperature of the system is lower than the temperature of the environment. T sub S is less than T sub E. Then experiments show that there will be energy transferred as heat, and this little schematic and the arrow shows you the direction of that energy transfer as heat, Q, from the environment into the system. Here an example might be a block of iron that had been in some freezer, a very cold cooling device for a while, and then is put into a regular room at room temperature. Now the temperature of the system is less than the temperature of the environment, and the direction of energy transfer is out of the environment and into the system. Okay, so in the first picture, the sign convention we will use when the direction of energy transfer as heat is out of the system, the Q will by definition be a negative quantity in joules. In the middle case, where the system and the environment have the same temperature, i.e. thermal equilibrium, there'll be no energy transferred as heat, so we would denote that as Q equals 0. And in the third case, where the direction of energy transfer is into the system, we will use the sign convention that Q will be a positive number in joules. So it's very important to keep track of that sign convention for heat energy, Q. Under what situation is Q a negative value? Under what situation is it a positive value? And under what situation is it equal to 0? Okay, you need to also be aware of an old-fashioned unit of heat energy that was used for many years while experiments were being done to study the phenomenon of energy transfer as heat, but before scientists really fully understood what heat energy was or how to think about it. And this old-fashioned unit of heat energy, you just have to be aware of because there might very well be problems that use it. It's called the calorie, C-A-L. This is the scientific calorie, not the nutrition calorie. The scientific calorie, little c-A-L is the unit. It's not the SI unit of heat, but it is an old-fashioned unit you'll come across. Here's its definition. The heat energy needed to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. It's just defined that way. You don't really need to memorize that definition. I'm never going to ask you to write that down. But what you do need to be aware of is that there is a simple conversion factor between the unit of heat energy, calorie, and the SI unit, joule. Just be aware of this conversion factor. 1 calorie is defined to be 4.1868 joules. And then you can just convert, if it's given in calories, into joules. All right, so we've introduced the idea of heat energy. Now let's talk about how we use it quantitatively in studying systems. Okay? All right. So the next kind of mini section here is we're going to introduce 3 new quantities. It can get a little confusing, so pay attention, and you can always go back and review this video as many times as you need to, or read section 18.4 in your book. But we're going to talk about heat capacity, specific heat capacity, and what's called heat of transformation. So let's start with a kind of overarching question. Let's ask, what can happen to a system when it exchanges heat energy with its surroundings? This kind of thing is going to happen quite often, quite frequently. We're going to have a system, it's going to have surroundings, environment, and it's quite likely that there's going to be an energy exchange as heat, Q, between system and environment. What kinds of things do we observe happen to the system? Okay. All right, I'm going to talk about 2 of those things here. This does not exhaustive list. There could be other things. Here's probably the most important one. 1. If the system is not at what's called a phase change point, then the temperature of the system can change. Then we have to unpack that. Phase change point. Phase change talks about phase of matter. The three common phases of matter that you're likely to find around you every day are, as you probably know, solid, liquid, and gas. And so a phase change point is when you are right at the boundary for a given set of ambient conditions between one phase and another. For example, as is pretty well known, for water at atmospheric pressure, 0 degrees Celsius is the boundary between the solid and the liquid phase. So we would call 0 degrees Celsius at atmospheric pressure a phase change point for water. We're saying if you're not at one of those special points, phase change point, and your system exchanges energy as heat Q with its surroundings, it's quite likely that you'll observe the temperature of the system change. Not 100% guaranteed, but quite likely. In this case, we need an equation to relate the energy transfer as heat Q and the temperature change, delta T. And it turns out experiments show it's very simple. They're directly proportional. The energy exchange as heat, Q, is directly proportional to the temperature change that occurs, delta T. Meaning, double Q, you'll double the temperature change, delta T. And then all you have to do is introduce a proportionality constant to get an equality. And that's this expression right here. Q equals capital C delta T. Q, of course, is the energy exchange between the system and its environment. Q is a positive value when energy enters the system as heat, and Q is a negative value when it leaves the system as heat. Delta T means temperature change. Emphasize change. And of course, delta change in something, delta T means T final minus T initial. And then the proportionality constant between Q and delta T has its own name. It's not a good name, by the way, but we're stuck with it for historical reasons. It's called the heat capacity of the system. I don't like it at all. Most physicists do not. It implies the system has the ability to store heat. You can't talk that way about heat. Heat is not something a single system contains. But nevertheless, that's the proportionality constant between Q and delta T. Q, of course, would be an SI unit of joule. Delta T would be in the SI unit of Kelvin. So the SI unit of heat capacity is joule per Kelvin. Now, heat capacity, capital C, depends on a couple of things. Well, a few things, technically. What is the material of the system? Just what is it? Is it a simple element like aluminum? Or just what is it? How much of it is there? Is it a little block of aluminum or a big block of aluminum? And technically, it also depends on the ambient conditions, like the temperature. But we're going to ignore that because that's not a huge determining factor. So mainly, what is the material and how much is it? How much of it is there? If you give the exact same amount of energy as heat, Q, to a small block of aluminum and to a very big block of aluminum, the small block of aluminum, not surprisingly, will experience a larger temperature change. That's a little bit of what makes heat capacity, capital C, a little bit of a pain to deal with. Because not only is it just the material, but how much? And you could have samples of aluminum of all kinds of different sizes. So what we would really like, okay, given that heat capacity depends on the amount of matter making up the system, we want an intrinsic property of a substance. Just tell me what it is. Is it aluminum? That's all I need to know. So we'll do that by taking our heat and temperature change equation we've introduced and just making one little change. We're going to multiply and divide the right-hand side by the same quantity, thereby not changing the equality. And that quantity we're going to multiply and divide by has to be some convenient way for us to measure the amount of matter. Whatever is convenient for us. One of the most common things is just, what's the mass of the system? If it's a piece of aluminum, mass it on a pan balance, please, and just tell me what's the mass in grams or kilograms. Tell me the units. So let's use the symbol M for the mass of the system. And we'll take that formula, the first formula, and we'll multiply by the mass of the system and divide by it. Thereby, I haven't ruined the equality. And then take this quantity that I've got in parentheses, heat capacity, capital C, divided by the mass of the sample, and let's just name it to a new constant. Now be careful, it sounds a lot like heat capacity. That's where the confusion can come in, okay? But it's not, it's a new thing. It's called specific heat capacity. See, the name is very similar, but that adjective at the front is all important. Specific heat capacity. Symbol, lowercase c. Yes, it's confusing because we got to be really careful. Lowercase c means something different than uppercase c. And you can think of it as the heat capacity, capital C, divided by the mass of the system, the sample. So in a loose sense, specific heat capacity is heat capacity per unit mass. And if heat capacity, recall, had unit of joule per Kelvin, and now what we have is heat capacity per unit mass, the SI units of specific heat capacity are joule per kilogram Kelvin. And with that new definition, we get a new version of the heat exchange temperature change formula right here, which is a form we will use rather frequently in solving some problems in this chapter. Q equals m little c delta T. Energy transfer as heat, Q, equals the mass of the system, little m, the specific heat capacity of the system, little c, times the temperature change. Okay. So little c, specific heat capacity, is just material dependent. You can look it up in tables. You'll find them in your book in chapter 18. That's what this symbol here means. This is material dependent, okay? You can look it up. For example, if you look up in your book the specific heat capacity of iron, little c, iron, you will find the number 450 joule per kilogram Kelvin. It takes 450 joules of energy to raise the temperature of 1 kilogram of iron by 1 Kelvin. Note, by the way, you might also see this unit K written as Celsius degree, because we're talking about a temperature change here, delta T, and therefore you can use either Kelvin or Celsius degree. This is technically, by the way, the value of the specific heat capacity of iron at room temperature. All right. Now, I said that we could make the very first formula on this slide more user-friendly by multiplying and dividing by some measure of the amount of material, the amount of matter. And I said, let's just use the mass. But there's other ways to denote amount of matter. Okay? One of the common ways that chemists do it is how many moles of a material you have. And we'll use that sum as well, especially when we talk about gases. But you can use it, of course, for anything. It's just a counting mechanism, a way to denote how much matter you have. So what you could do is take that very first formula, Q equals capital C delta T, and multiply and divide the right-hand side by a different measure of the amount of matter, the number of moles. And your book symbol for the number of moles of a material is little m, number of moles of the system. And I'm going to talk a little bit more about that in the in-class video, number of moles, a brief reminder. But for now, you just basically need to remember, when you're working with number of moles, another important number that's called Avogadro's number. Your book's notation for that is capital N sub capital A for Avogadro's number. Very famous number in physics and chemistry. Avogadro's number has the value 6.02 times 10 to the 23 units per mole, where the word units there is in quotes because it's not really a official unit. It's just how many objects there are in a mole. There are 6.02 times 10 to the 23 objects in a mole. Okay, so if we multiply and divide by the number of moles of our system, using the symbol little n, okay, we can do that. It's a measure of the amount of matter. Now let's introduce a new constant. Ready? It's going to be capital C over N, heat capacity divided by number of moles. And that's going to be called, okay, watch out, the molar specific heat capacity. So now there are two very important adjectives out front. Molar and specific. Molar specific heat capacity of a system. I like to denote it as little c subscript molar. And it's the heat capacity, capital C, divided by the number of moles. And so if molar specific heat is heat capacity per unit mole, then the SI unit of molar specific heat capacity is joule per mole Kelvin. MOL is an SI unit for amount of stuff, amount of matter, MOL. And so if we use this new kind of specific heat, the molar specific heat, in the Q delta T formula, it looks like this right here. Q equals little n, little c molar times delta T. Q equals the number of moles times the molar specific heat capacity times delta T. We'll be talking about that as we go on into chapters 18 and 19. But I want to introduce that to you now. Okay, so again, the question was at the beginning here, what are some things that can happen when a system exchanges energy as heat, Q, with its surroundings? And we said, one, if we're not at a phase change point for the system, then its temperature can change as the heat exchange occurs. Now we're going to possibility two. What if the system is at a phase change point? What if I have water at atmospheric pressure at 0 degrees Celsius? Let's say it's liquid water. If I let energy exchange out of the system as heat, Q, out of the water into the surroundings, I discover, since I'm at this special point called the phase change point, the water's temperature does not go down in a regular standard sample of water. It does not go down. Instead, that energy transfer out as heat is allowing the system to rearrange its water molecules into a different configuration, a crystalline configuration. We call it ice. Okay? All right, so if we're at a phase change point, of course we have to know if that's the case, but if we're at a phase change point, any heat energy that is exchanged between the system and its environment goes to produce, to allow the phase change to happen, not to change the system's temperature. So if you have a sample of water right at 0 degrees Celsius in atmospheric pressure, and you take energy exchange outward into the environment as heat, you will not discover that the temperature of the water goes down. Instead, it starts to undergo the phase change. We call it freezing. Okay, so now there is no delta T. If we're at a phase change point, no delta T until the phase change is complete. Okay? But there is still a very quantitative, useful formula that you get from experiment. And now, the energy exchange is heat. There's still Q, there's just no delta T. Is going to be proportional to that mass of the system that actually undergoes the phase change. So now the proportionality is that Q is proportional to M, but be very careful about what that M means. Okay? The M in that formula is the amount of the sample M that has undergone the phase change because of Q. Okay? That's the mass of the system that has undergone the phase change. Okay? Okay. Now that's a proportionality between the energy transferred as heat and the amount of mass that underwent the phase change. So all I have to do is introduce a proportionality constant. And that's this next formula right here. And the proportionality constant is a symbol capital M, and it's got a name. Again, it's not a great name, but it's what we use. It's called the heat of transformation of the system for the particular phase change. The heat of transformation. Not a great name, but that's what it's called. Of the system for the particular phase change. Now, of course, in terms of units, Q is in joules, if we're talking SI. M is in kilograms. So the SI unit of the heat of transformation must be joule per kilogram. Now, let's just be clear about the common phases of matter and the names for the various phase changes that occur. Here's a little diagram, schematic diagram, that represents the three common phases of matter that we will be dealing with. As you are aware, solid, liquid, and gas. And between any two of those phases of the material of matter, you can have a phase change from one to the other directly. And there's a name for each kind of phase change. And the energetics of the kind of phase change differ. So for example, going from solid to liquid, as you probably know, is called melting. Or you can go from liquid to solid, the other way. That, of course, is called freezing. Either one of those two together, melting or freezing, has its own heat of transformation. And it's called the heat of fusion. And the symbol we use, I'll write it right here, it might be hard to see. It's capital L sub F, the heat of fusion of the material. Then we're talking about the phase change between solid and liquid, whether it's going from solid to liquid, melting, or from liquid to solid, freezing. The corresponding heat of transformation is the heat of fusion in joule per kilogram. So if you have a solid right at its fusion phase change point, you need to know the heat of fusion for that material to know how many joules of energy as heat you'll have to add to melt 1 kilogram. Or, if it happens to be in the liquid phase, at the phase change point, how many joules of energy as heat you'll have to extract to freeze 1 kilogram. By the way, the name fusion has nothing to do with the nuclear process, also called fusion. This does not have anything to do with a nuclear process. Fusion is just a name for the solid-liquid boundary. All right, what about the liquid-gas change? Okay, now you can go from gaseous phase to liquid phase. That's called condensation. Let me highlight that right there. Gas phase to liquid phase is condensation. Liquid phase to gas phase is called vaporization. Either one of those, the appropriate heat of transformation, is called the heat of vaporization, which I will denote capital L sub V. And that'll be a constant for a given material in joules per kilogram. Please note, for a given material, again, maybe you want to think about water. The heat of fusion for water, L sub F, and the heat of vaporization for water, L sub V, not the same. Why is that? Because it takes different amounts of energy to undergo the fusion phase change than the vaporization phase change because of how the molecular arrangements are different in the various phases. Now, the last combination of phases is solid and gas. And you may not be quite so familiar with phase changes between those two directly, but they can happen. So to go from a solid directly to a gas, that phase change is called sublimation. Okay. Dry ice is a common example of a material. Dry ice is just solid carbon dioxide. That material happens to go at atmospheric pressure directly from the solid phase, dry ice, solid CO2, to the gas phase, gaseous CO2. by sublimation. It also happens in your freezer. If you've had a tray of ice cubes and you leave them in there a long time, you'll find that the level of the ice goes down slowly because the solid ice is sublimating into water vapor. Doesn't happen very fast, but it happens slowly. To go from a gas to a solid, that's called deposition. To go directly from a gas to a solid, that's called deposition. Probably the most common example of that happening is frost. When gaseous water solidifies directly on a cold substance. Deposition. Either one of those, if you have that kind of transformation going on, the heat of transformation is called the heat of sublimation. Capital L sub S, also in joule per kilogram. We're not likely going to bump into that, but it can happen. Okay, so mainly what we've learned now is that we can deal with energy exchanges as heat between a system and its environment quantitatively with equations if, one, we're not at a phase change point and the temperature of the system changes, or two, we are at a phase change point and the system is undergoing a phase change. So I'm going to end this video with a little discussion of some practice that then you're going to get to continue with on Blackboard. Okay? The kind of picture that your book uses to tell us a physical story of what might happen when a system and its environment exchange energy as heat. It draws a graph. Well, we love graphs, right? Graphs are a great way to tell a quantitative story. So here's the practice. Let me describe the situation. We have a sample of liquid water, call that A, and a sample of ice, call that B. They have exactly the same mass in grams or kilograms. They are placed in a thermally insulated container, so they can only exchange energy as heat between each other, and everything else around them is isolated away, gone. And they will, because of a temperature difference between them, the water is going to have a higher temperature, the ice is going to have a lower temperature, they're going to exchange energy as heat until they come to thermal equilibrium. You wait long enough in a situation like this, and that will guaranteed happen. They will come to a common final temperature. Now this figure is a sketch graph of the temperature, now watch out the symbols, capital T, as a function of time, little t. Temperature versus time for both samples. A for liquid water, B for ice. I want us to be able to take that kind of a graph and tell a story in words of what is happening in that container, and then answer the questions below. Okay? There is a lot of information in a graph like this. First of all, you have to be able to identify what in the graph represents the water and what represents the ice. Well, why don't we look at time zero here? This clearly, right down here, is time zero when the graph begins. Can you tell which part of the graph represents the water and which represents the ice? Well, it's got to start right up here for the water because that's the higher temperature initially. There's the dot representing the temperature of the water. And there's the temperature of the ice. And they clearly are at different temperatures, but they are in contact so they can exchange energy as heat. And you obviously know which way the energy transfer will go, from the higher temperature object to the lower temperature object. So from the water to the ice. As a result, as the clock ticks away, little t, the temperature of the water starts to go down. So that's this part of the graph right there. And the temperature of the ice starts to go up. So that's that part of the graph right there. Note, if you look carefully, that those two line segments have different slopes, different rates of change of the temperature. Simple reason for that, water, by which we mean liquid, and ice have different specific heat capacity. I'll let you think about which one has the larger and which one has the smaller specific heat capacity. Okay, nevertheless, temperature of the water goes down, temperature of the ice goes up, until you get to a rather important point, which I'll mark with a dot, right there. Because after that, look what happens to the segment representing the ice. Its temperature is now flat, constant, unchanging. So do you see what the story is telling you has happened? When you get to that point where the red dot is, what temperature has the ice reached? 0 degrees Celsius. Let's assume we're at atmospheric pressure. Right? The phase change point, the freezing point. And now, note though, that at that moment in time, when the ice reaches 0 degrees Celsius, and therefore the ice is at that point on the red dot, go vertically up, the water is still at a temperature above 0 degrees Celsius. So the temperature of the water is still greater than the temperature of the ice. So there will still be an energy transfer as heat, away from the water and into the ice. So the temperature of the water will continue to go down. But the temperature of the ice will not go up. Instead, the energy that's coming into it is causing phase change to happen. The ice is starting to melt. And it takes energy to do that. The water is providing it. So now go across a little bit. The flat part for the ice says it's still undergoing phase change, still melting. And therefore the temperature of the water still goes down. And the next key point I'll mark with another red dot is right there. When the water reaches 0 degrees Celsius. Now I have ice and water at 0 degrees Celsius. Everything's at the same temperature. Guess what? We have thermal equilibrium. And therefore, after that, no more temperature changes because there's no more energy exchange as heat. The story is over now, folks. All the energy exchanges have occurred. Nothing else is going to change. Remember, this thing is in a very insulated container. Okay? So we can read that graph and tell you a story of what happened. Now let's answer those questions. Is the equilibrium temperature above, below, or at the freezing point of water? Well, we know it's at the freezing point. It's at 0 degrees. That's pretty clear. It's at the freezing point of water. The graph shows me I get to the freezing point. That's where the temperature graph for the ice levels off, and it never goes above or below that afterwards. B, in reaching equilibrium, does the liquid partly freeze, fully freeze, or undergo no freezing? Well, the liquid gets down to 0 degrees Celsius, right? And but before that, it's all liquid water. And the minute it gets to 0 degrees Celsius, there's no more energy exchange because everything's at the same temperature, thermal equilibrium. If there's no more energy exchanges, period, then nothing more can happen to that water. Nothing. So we are left with all that still being liquid water. Understand? So it undergoes no freezing. It gets right down to the freezing point, but there's no temperature differences anywhere anymore. Okay? So there isn't any more energy exchange. So nothing more can happen to that water. All right, so the liquid, no freezing. Lastly, does the ice partly melt, fully melt, or no melting at all? Well, we know it undergoes some melting, doesn't it? Because it gets to 0 degrees Celsius before the water does, and so you get this flat part while the water is still providing energy. The question that's a little bit subtle with these kind of graphs, and I wish, well, it's just a little bit subtle, is, has the ice fully melted or only partially melted? And I suppose the only way to know if the ice had fully melted is if the graph had been a little bit different than this. Let me try to sketch it over here to the side. Temperature versus time. Let's just do the ice part. Goes up in the ice phase, undergoes the phase change, so there's no temperature change. And if it had fully melted, completed its phase change, and there was still some warm water, its temperature would start to go up again. Meanwhile, the water graph would come down and eventually meet it. So the point is, if I'd had a bit like this at the end, showing that the ice had gone up above its plateau, then I knew the ice had fully melted into water, and that water was then warming up. This picture doesn't show anything like that. So we're going to say that the ice partly melts based on that graph that we're given. So we are left with a mixture of ice and water at 0 degrees Celsius. And if you've got a glass with ice and water together, then you know they're both at 0 degrees Celsius, if it's staying that way, okay? If the ice is no longer melting. So that's a pretty interesting way to tell a story. It's a scientific way to tell a story about putting two materials together, letting them exchange energy as heat, and talking about what things we observe happen. So what I want you to do for our class engagement on Blackboard is tell a similar story for a number of other graphs. So here are 4 more graphs of temperature, capital T, versus time, little t, for more samples of ice mixed with water, same amount of mass of each. For each sample, write a couple of sentences telling the story of what happens. For example, is the equilibrium that is attained at the end above, below, or at the freezing point of the water? As the equilibrium is reached, does the liquid partly freeze, fully freeze, or undergo no freezing? And does the ice partly melt, fully melt, or undergo no melting? So you do that for graphs B, C, D, and E. We did graph A together just now. So you do that for graphs B, C, D, and E. Okay? And then we'll have a class video where I will talk more about using the formulas I've introduced in this video. But that's all for now.